Last sec, guys. E&M set 2 for the 2023 AP Physics C exam. We're almost there. All right, now this set I haven't actually solved. I'm actually doing this blind with you guys. The other ones I've taken a look at, gone through and actually done some solutions for them, but this one's going to be blind. So we'll see how it goes. I'm pretty confident with it. In the sense of like they're not very different between set 1, set 2, so it should be similar concepts that we're going through. All right, but anyway, in this case, it looks like what we have is two spheres again to determine vacuum permittivity. Sphere A is non-conducting with an insulating rod. Sphere B is non-conducting as well. And sphere B rests on an insulating platform with a vertical ideal spring. Everything is initially at rest. So you bring sphere A near this sphere B without them touching. And when they are separated by a distance h, the spring is compressed vertically. And so we're trying to measure y and h together. All right, so let's go ahead and move on to the next page here. And it looks like what we have for the very first question, I do actually have a paper copy with me so I can read it without moving my sidebar too much. On the following dot that represents sphere B, label and draw the forces acting on them. Each force must have a distinct arrow pointing. It's a free body diagram, guys. So obviously we're going to have two forces pointing down, gravitational force as well as as well as electrostatic force. So we're going to have weight force. All right, I apologize. My tablet is lagging a little bit. Give me just 1 second and I will be right back. All right, sorry about that. I'm back now. Yeah, the tablet was freezing up because I was actually exporting my video for the Set 1 FRQs, so just being a little bit too ambitious there with my computer. But all right, we're back now. Let's go ahead and finish off these FRQs here. So we do again have weight force pointing down, right? In addition to that, we've got some electrostatic force pointing down as well. So that's going to be important. And then finally, we do have spring force as well. Now that spring force should be equal and opposite both of the other forces due to this object being in equilibrium. So very important there too, right? Make sure you get the correct magnitudes. Good. In terms of the next thing, right? Derive the relationship between y and h. We can do that just by using net force is equal to 0 again, right? So what that tells us is that ksy is going to be equal to, that's going to be equal to mg plus the electrostatic force, right? So everything up equals everything pointed down. So we get QQ over h squared. Oh, wow. That's actually not too bad. You just divide both sides by KS and you're there. All right. Nice and nice and difficult there, guys, right? All right. Okay. Well, that was a little bit underwhelming. All right. I could see how people would overcomplicate that, though. I actually overcomplicated a question on mechanics last year, and it took me forever to figure out what I did wrong. One of the reasons why I kind of think about net force as 0 is because we're told equilibrium and because we already did our free body diagram, though. All right, okay. Anyway, moving on to part C, draw the best fit line. You can go ahead and draw yours. I'm just going to give you my slope again. My slope was equal to 0.002. Where that came from is it came from using the points 5, 0.12 and 15, 0.14 on the graph. Again, everybody's slope's going to be a little bit different. All right, using the best fit line, calculate an experimental value for the vacuum permittivity given both of the charges and the spring constant. So here in this case, as you guys might be able to expect, right, y over 1 over h squared should be the slope. Now, with the equation that we have back on the left page, it's a little bit more difficult to actually analyze how the slope relates to that. But you can see that this kind of looks like y is equal to mx plus b, where x is equal to 1 over h squared in that case. Therefore, what we can say is that the slope also has to equal 1 over 4 pi epsilon naught times the product of charges divided by the spring constant itself. That should be our slope. Therefore, if I'm looking for vacuum permittivity, I should get QQ, right? Both Q's over 4 pi Ks times the slope. So in terms of this, what that would actually go ahead and give me is some value. I'm doing these blind, so I haven't actually computed it. So I'm just going to actually go ahead and put the calculation up here for you to go ahead and try out if you want to as well. Again, you do need units as well. The units are on your equation sheet, but it does end up being, I do believe, meters to the negative third, kilograms negative first, seconds to the fourth, and amperes squared. And again, it's on your equation sheet in a different format. Use whichever one you want. 4 pi times 25 times 0.002. So that should give you an answer around what the actual epsilon naught is. It should give it to you on the same order of magnitude. Good. Using the best fit line, calculate an experimental value for the mass. Well, mass appears in the y-intercept of our equation on the left, right? So we can say that the y-intercept is going to be equal to mg over ks, right? Well, what is the y-intercept? If you draw the line that I used for my slope, the y-intercept would have been approximately 0.105. So 0.105 would equal mass times g, which is 10, divided by the spring constant, which is 25. So 0.105 is equal to 2/5 mass. Or in other words, right, mass is going to be equal to 5 times 0.105, all divided by 2. And that would be in terms of kilograms then. So good. I don't actually think that we're going to need these values in the next page. I could be wrong again. I'm doing these blind. Yeah, you don't. I'm looking at it right now in my paper. So in that case, right, you can go ahead and plug them in just to see what I got and check to see if it's something around there. I'll go ahead and do the mass for you guys actually, because that one's not too bad. So if we take a look at our mass, it's 5 times 0.105 divided by 2. Okay, so for the mass, I got 0.26 kilograms. And actually, while we're here, let's just go ahead and do the epsilon naught as well. That way you guys don't have to worry about it. Okay, 0.0000002. I'm just using my phone calculator, so I apologize. 0.0000002. And then I divide by 4, divide by pi, divide by 25, and then finally divide by 0.002. Okay, so the value for epsilon naught that I got, if you plug everything in, is going to give you 6.4 times 10 to the negative 12th, which is on the correct order of magnitude, a bit less accurate than I got in the first set, but still pretty decent. So good. All right, moving on to the next page then. Let's go ahead and finish up question number 1. The students modify by placing a non-conductive, by changing sphere B, which is the one touching this spring, with a conducting sphere sphere C of same charge and mass. So you compress the spring, sphere C comes to rest, and much like in the previous case, what you're trying to do is you are trying to, it looks like what you're trying to do is figure out how the vertical distances that the spring compresses change. So it says that both spheres are the same vertical distance. I apologize. Okay, so I'm reading this, and it says that spheres A and B and A and C are both h1 apart, and you're trying to figure out how y1 and y2 compare. Oh, okay, I see. So there's still the same distance apart, like the actual spheres are, but it doesn't look like the spring's going to compress the same amount. And I would not expect it to compress the same amount, because keep in mind that sphere A is positively charged. So much like in set 1, I would actually expect a lower compression here. So y2 would be less than y1 for the same reason that we had last time. Just to reiterate, right, on average, there is a lower electrostatic force. And if there's a lower electrostatic force, And I'm going to explain why as well too. The reason why is because the negative charges and positive charges both redistribute themselves, right? Because this is a conductor now. There we go. They both redistribute, right? And so that's going to mean that the negative charges are closer to sphere A, and the positive charges are farther from sphere A on sphere C, right? Both of these are on sphere C. So in terms of that, you would absolutely expect that on average you have more attraction and less repulsion, right? I don't know how much exactly. Obviously, that would depend on how good a conductor we have, but it is going to lead to a lower repulsive force, which is what we were dealing with before. So if there's a lower electrostatic force, right, that's going to mean that the spring force decreases as well, because the spring force was counteracting the electrostatic force. So let me actually explain this a little bit more just in terms of words to show you how you might word it, right? Negative and positive charges both redistribute, leading to more attraction and less repulsion than in the first case. There we go. All right, that sounds good. All right, perfect. Sphere C is then grounded with a wire. On the following figure indicates the direction that the platform will move immediately after being grounded. Okay, so the spring is partially compressed, and what I would expect is I would expect for the positive charges to, sorry about that. I would expect for the positive charges to actually leave the sphere C. And in that case, sphere C is going to remain negatively charged. And so what's going to happen is the platform should end up moving up because sphere C is going to attract. So the platform is not going to remain stationary, but it is going to be moving up then. Good. All right, and that does it for question number 1. Okay. So let me go ahead and erase all of that, and we'll go ahead and move on to question 2 now. Question 2 is another rail gun-ish problem, right? Two parallel conducting rails. You have a conducting bar and a resistor again as well, too. Oh man, okay, so it looks like at time t is equal to 0, it's released from rest. T is equal to 1, it enters the field. At the bottom, T2, it enters no magnetic field. T3 enters the second field, and T4 leaves the field again. Okay. Oh, wow. That's a lot. That's a lot of intervals. So we're looking at the times between T1, T2, which is when the field is pointing up, right, out of the up in the perspective view, out of the page in the top view. So let's go ahead and move over to the next page, and let's go ahead and actually answer this question. On the following diagram is, as observed in the top view, draw an arrow indicating the direction of the net force. So this is very similar to set 1 again. And so what we're going to end up having is an increased magnetic flux through the actual area, right? And it's going to be perpendicular to the area. So in that sense, that flux is going to be pointed out of the page this time. Therefore, the current in this case is actually going to be clockwise from the top view. Because again, more flux out of the page. Lenz's law predicts that the induced current is going opposite of where it would if it were going in the direction of, if it were consistent with the right-hand rule for the real change. So induced current is clockwise. That means that from the top view, it's going down through the bar. And so by the Lorentz force law, the net force should be pointed to the left. So the bar is going to actually be slowing down when it enters this region of magnetic field. All right. At time b, TB, the speed of the wire, compute the magnitude. You do this much the same as set 1 as well, too. This is kind of nice. I guess that I'm doing this blind in the sense of like it helps me kind of look at this a little bit better too. All right, so that's going to be the change in flux with respect to time, right? Keep in mind that field is constant in this region, so change in flux is just going to be b dA dt divided by resistance, right? And then the actual area in this case is going to be b times L times dx dt divided by r. So we end up with our familiar from set one if you've watched that. If not, no worries, right? But you end up with this expression for the induced current, BLV over R. B is equal to 0.4, and I'm just going to do this calculation as I'm speaking. So 0.4 for the magnetic field. The distance, sorry, D and L are the same thing. I'm actually sticking to notation from the first set again. D and L are the same. Right, that's the length of the loop. So D is 0.3, so 0.4 times 0.3, velocity is 2.5, so I'll multiply that in, and then I will go ahead and divide by resistance 0.2, and I do believe that gives us 1.5 amps of current. Good. Calculate the magnitude of the field. Well, that should just be BID. So that's going to be 1.5 times 0.4 for the field, and multiply that by D, which is 0.3, and you get 0.18 newtons. All right, sketch a graph for the speed as a function of time, right, between the entire thing. So from t0 to t1, we're going to be speeding up with constant acceleration because we're just going down frictionless rails. So in terms of that, you would expect a linear increase, right? Because that's due to just acceleration due to gravity down the ramp, right? Mg sine theta. Now, when you reach the second part, you're going to go ahead and have exponential decay because of the induced current, right? Force is proportional to current, right? And current is proportional to velocity. So it's much like air resistance slowing something down. Good. T2 to T3, nothing. T2 to T3 is nothing because there's no magnetic field. Good. Now, and so therefore there's no change in flux from T2 to T3. Now, when we're going from T3 to T4, the field is actually pointed down from the top view. Now, if the field is pointing down from the top view, that's actually not going to cause a change in flux. And therefore, actually, if I'm not mistaken, from T3 to T4, you're also going to have a constant velocity, actually. So it's a linear dependence because, for the first part, again, because force is proportional to g, right? And therefore, velocity is going to be proportional to g times time, right? Meanwhile, for the second part, it's this force proportional to I proportional to v. And then for the other two, it's going to be constant velocity because there's no more change in flux. And therefore, there's no induced current either, right? So it's just going to continue with the velocity that ends with after T2. That's interesting. I actually really like that. This is a fascinating problem. All right. Okay. Moving on to the next situation, you're replacing it with a new bar, but with non-negligible resistance. And you're trying to determine the total resistance first. Well, because the two things are in series, right, it would be that the total resistance is just going to be resistance of the bar plus the actual resistance itself. Bar's resistance is 0.2, which is actually the same as the other one. So it's just going to be 0.4. You add them both together and you get 0.4 ohms. All right. Good. In the original scenario, okay, so this is the same as set one again. You're trying to figure out with this new resistance, do you have a greater, less, or greater, lower, or equal acceleration to the original case? And in terms of this, you would have a lower, yeah, this one would actually be a lower acceleration, like I thought originally for set one. The reason why it's lower is because a higher resistance decreases the induced current. And if you decrease the induced current, right, that's going to decrease the net force, which is again due to the Lorentz force law. Therefore, acceleration drops. There you go. Nice, easy, nice, short and succinct explanation there, right? Lower acceleration. Describe a modification to H, B1, or D that would result in a larger induced current. Well, what we do know is that if you were to, we do know that induced current is given by BdV over R, right? That was given back in part B. So you could actually change any of those, right? It's just asking you to describe one modification. What I'm going to say for this one is I am going to say that what you could do is you could increase H, right? And you could really increase any of these, right? But if you increase H, this causes the bar to move faster when it enters the first region with field. Therefore, the flux changes faster, yielding a higher voltage and therefore higher induced current. Right, that's a nice one. You could increase B or D as well too, and either of those would work. You would just have the same justification as well too, except it wouldn't cause the bar to move faster. It would only just increase the change in flux. Right, so you would just get rid of that second sentence that I have. Good. All right, let's go ahead and move on to the next part. Oh, wow, we're already on question 3. I think that one was easier than it was in set 1. I was actually expecting a little bit more, but okay, I'm down for it. All right. Okay, so this one looks very similar to what we had in set 1 as well, but now instead of 2 resistors in parallel, we have 2 resistors in series. All right, so both resistors have the same resistance, and both capacitors actually have the same capacitance as well. Right, but do not solve a differential equation if you close the switch with A. All right, Kirchhoff's loop rule, right? Every time you have a differential equation in E and M, it's got to be Kirchhoff's loop rule. That says that E minus, the current's going to be the same through both resistors, so I times 2R, right, because that's the equivalent resistance now, minus Q over C is going to equal 0. I is equal to dq dt. So we get E minus 2R dq dt minus Q over C is going to equal 0. There's your differential equation with respect to, for charge with respect to time. Good. All right, moving on to the next one, sketch graphs for the current and the energy stored in the capacitor. Well, current should decrease exponentially because the capacitor is going to generate its own current to oppose that of the battery, and it's going to slow down. So this should actually be an exponential decay, not an inverse. Sorry, exponential decay. Again, apologies for the bad graph. My tablet's still lagging a little bit. I can't fix it. It's due to how much processing power I have going on. But yeah, current should decrease exponentially. That's a trend that we should be pretty familiar with. Now, in terms of thinking about energy stored, right, energy is going to be proportional to charge squared, right? And we do know that charge should go like 1 minus e to the negative t over tau. So in this case, you should expect for the energy to rise pretty quickly and level off exponentially as well, too. All right, now capacitor 2 is uncharged, C1 has Q naught, and then you move it to you move the switch to position B. Immediately after you do that, is the direction of the current through resistor 1 up, down, or no current? It has to be up. And the reason why is, you guessed it, same as set 1, right? The upper plate of capacitor 1 is positively charged, and lower is negative. So current goes clockwise. Therefore, it has to go up through R1. Determine the amount of total charge on capacitor 2 a very long time. Well, the reasoning for my justification for this is that both capacitors have to have the same potential difference a very long time after you have closed the switch. So that implies that Q1 over C is equal to Q2 over C, right? And both Q1 plus Q2 have to equal Q naught because of conservation of charge. Therefore, it follows that Q1 and Q2 are actually going to be the same because the capacitance is the same. They're both Q naught over 2. Good. All right, moving on to the next question. I'm actually really liking this set. It's actually really interesting, and I actually really like it. So let's move on to the next page. I'm sure we'll have some more difficult stuff coming up for me. I seem to struggle on the very last few parts. So good. Derive an expression for the total energy dissipated by resistor 1 immediately after until steady state has happened. So the initial energy that we have is just on capacitor 1, which is Q naught squared over 2C. The final energy that we have is on both capacitors, and in both cases you've got Q naught over 2 all squared, divided by 2c. So that's going to give you q naught squared over 8c times 2. So therefore, your final energy is q naught squared over 4c. Therefore, the energy dissipated, right? Let's call that just E is equal to the amount lost, Ui minus UF. So it's going to be Q naught squared over 4C, right? That's going to be your energy dissipated. While the switch is closed, you insert a dielectric material K equals 2, kappa equals 2, into capacitor 2 and determine the charge on the positive plate a very long time after the dielectric. Well, if you insert a dielectric equal to 2, that's going to cause C2 to double because it doubles linearly with the dielectric. It scales linearly with the dielectric constant. So therefore, it becomes 2C instead of just C. That means that in order for both capacitors must get the same potential difference again, right? V1 has to equal V2. That implies now that Q1 over C has to equal Q2 over 2C. But remember that Q1 plus Q2 has to equal Q0. Therefore, Q2 has to equal 2Q0 over 3, right? Leaving Q1 as half of that as Q0 divided by 3 and maintaining conservation of charge. With the switch closed to position B, a wire of negligible resistance is connected to these 2 points as shown. All right, derive an expression for the current in resistor 2 immediately after the wire is connected. All right, so it looks like, ooh, interesting. This is an interesting one. It looks like what's going to happen now is capacitor 1 and the resistor are in series with each other, right? And then they're both in parallel with the capacitor 2. Oh, man. Okay, this is actually an interesting question. Let's just go ahead and maybe loop rule it. I think that would be a good thing to do, because we do know that capacitor 2, right, has a voltage given by 2q naught over 3, right, divided by its capacitance, which is 2c, right? That's going to equal its voltage, because it's charge divided by capacitance. So that's going to give us q naught over 3c. Now, if that forms a closed loop with resistor 2, which it does indeed, right, then that's going to mean that also has to equal the voltage on resistor 2 as well. So let's say that's equal to VR2 then, right, V sub R2. Well, that means that since V is equal to IR, right, that means that Q naught over 3C has to equal the current through resistor 2 times its resistance, which I think we said was R. So therefore, the current has to actually equal Q naught over 3RC. Interesting. That's a nice one. It makes you think about loop rule a lot. All right, determine the current a very long time after the wire is connected. Oh, goodness. Okay. All right, very long time after the wire is connected. So at that point, all right, so here's where things get to be a little bit difficult for me now, because unlike, I want to say what you would have is it would probably be 0 actually. I want to say it's going to be 0 amps, and I think hear me out. If you don't agree with me, hear me out. Or if you do agree with me, hear me out anyway. The reason why I think it's going to be 0 is because much like if you just have one capacitor and one resistor, the energy is eventually going to dissipate. Eventually, you're going to have to recharge that capacitor. In this case, the battery isn't part of a closed loop. So I think that a very long time after the wire is connected, you would end up losing all of your energy, just like in a simpler RC circuit. I'm going to stick with 0. I hope that made sense, and I hope you're convinced with that. And if we go on to the next page in my paper packet, yeah, there's nothing. So that's the end of set 2. All right. What an interesting set of questions, actually. I will say that I did actually kind of enjoy these questions. The E and M ones were really fun for me. Like, I know that they're a little bit difficult, and I think I struggled probably the most with the ending parts of question 3 on both of them, as well as that velocity graph in set 1. And then in mechanics, I struggled with set 1 question 2, definitely. Set 1 question 2 was probably the hardest of the 6 mechanics questions, in my opinion. As well as set 1 number 3 was actually a little bit tricky as well. It did take me a little bit of time to figure out the last few parts. But let me know what you thought. Let me know if you have any questions, comments, right, disagreements. I'm always open to explaining myself a little bit more in terms of how I solve these problems. So feel free to let me know. But thanks for watching, guys. Hopefully you find this helpful. If you guys are watching these sets of videos in the future in preparation for your C exams, best of luck on your C exams too. And yeah, hopefully this is very helpful and gives you an idea as to what to expect on the FRQs and what sort of reasoning to go through to think about all of these questions. Have a great day, everyone, and take care.